Good day everyone. I'm honored to present our research on the development of prediction models to detect MGMT promoter methylation in brain tumors, a crucial marker for prognosis. Brain tumors represent a formidable challenge in oncology, being the 10th leading cause of death. Our demographic studies highlight the prevalence across age groups, underscoring the urgent need for advanced diagnostic methods. Today, I'll introduce you to our innovative approach to predicting MGMT promoter methylation, a key to personalized treatment strategies. Traditionally, brain tumor diagnosis relies on a mix of non-invasive and invasive methods. However, these techniques can be time-consuming and, in some cases, risky. Our research focuses on a less invasive, more predictive model based on MRI sequences, offering a safer and potentially faster diagnosis pathway. MGMT promoter methylation status plays a critical role in the effectiveness of alkylating agent therapies. MGMT gene promoter is either methylated or unmethylated. If the gene is considered as methylated MGMT, it decreases the repairability of damaged cells, so the TMZ alkylating treatment is effective. If it is unmethylated MGMT, the gene will be able to fix the damage produced by TMZ, making TMZ less effective. Surgery, which is the only acceptable approach to identify the MGMT promoter methylation status, involves invasive techniques and might lead to serious consequences. It also can take several weeks to determine the characterization of the extracted tissue sample. Our objectives are clear: to implement data visualization and exploratory data analysis for a deeper understanding of brain tumor datasets, and to develop a predictive model using deep learning algorithms. After that, developing a graphical user interface for a user-friendly interaction between the user and the system. The scope includes extensive data analysis and the creation of a user-friendly GUI for real-world applications using deep learning algorithms after applying image pre-processing techniques. The existing gap in non-invasive detection of MGMT promoter methylation led us to this endeavor. By leveraging advanced deep learning models and comprehensive data analysis, we aim to close this gap, offering a novel solution to a long-standing problem. We've meticulously gathered and processed data, implementing sophisticated algorithms to ensure our model's accuracy. Our methodology, from data acquisition to deep learning application, is designed for optimal performance and reliability. Our dataset consisted of training and testing sets, with 582 samples, inside each sample 4 MRI sequences, T1W, T2W, T1WCE, and FLAIR, resulted in 347,280 images, and 82 samples in the test set with 65,851. It is worth mentioning that this is a large number of files, and we need to consider finding a way to solve it. In our training set, we have 276 samples as unmethylated MGMT promoter in a brain tumor, and 306 as methylated. So we divided our dataset into 4 sets corresponding to their sequence. We can see that T2W has the largest number of images with an average of 171 slices of images per sample case, and the lowest is FLAIR with an average of 124 slices of images per sample case. In our test set, we can see that T1W has the largest number of images, and the lowest is FLAIR. In image pre-processing step, we started with black image removal, especially from the start and end of the image slices of each sequence, which allows the model to focus on key patterns and features. Then we applied the value of interest lookup table to increase the contrast and visibility of regions of interest within the DICOM files. Then image normalization. Then image type conversion from N16 to UN8, which results in a smaller file size, while having the same image geometry which preserves crucial spatial information. Then resize the images, to reduce computational and memory requirements. As you can see, same image but smaller size. So these are the number of slices of images of the datasets we are using. The goal is to accurately classify the images into two categories, methylated and unmethylated for each sequence. The algorithms used in our research are ResNet 50 and EfficientNet-B2. Global average pooling, dropout, and dent are added layers. Also, the sigmoid activation function is used in the output layer for probability prediction. The loss function used is binary cross entropy. Worth noting that MRI image slices are treated as individual images and not as the slices of an image. To evaluate the performance of our models, we are using accuracy, precision, recall, and F1 score. The microaverage has been used, which aggregates the scores across all classes and takes their average. T2W modality outperformed other sequences, achieving a validation accuracy of 0.9453 for ResNet 50. It has the highest precision, recall, and F1 score with 0.95. Note that T2W images provide essential information concerning fluid accumulation, edema, and lesions, which is effective utilization of unique traits and patterns. The Bratz Arsenamici brain tumor radiogenomic classification study did not release its results of the testing set, limiting comparing and measuring the accuracy of prediction results with the actual results. As a result, a validation set has been utilized to analyze and evaluate the performance of estimations as discussed earlier. However, here are the probability values predictions of the test set. This is our interface. It contains an upload component that accepts DICOM files, then applies the necessary pre-processing techniques and make the prediction. Here is a live demonstration of the interaction. Let's try the examples below. First, we submit the image, then it will give us the methylation status and the TMZ effectiveness results, which will affect the treatment decision. The interface was developed to identify and alert users to invalid images, ensuring accurate analyses for informed treatment decisions. Thank you for listening. Have a nice day.